right, so in this unit, we're going to be looking at covalent molecules in pretty grueling detail, a little bit at ionic, but mostly at covalent molecules. And these molecules share electrons, and as a result, they have really unique, cool shapes that we're going to be looking at. And that then is responsible for all the different things that they can do, how they're attracted to each other, how we can then actually experience them. So we're going to be talking about taste and talking about spice specifically. We're going to be looking at how we can get rid of spice in our mouth, and all of that has to do with the shape that these molecules take. But in order to understand that, we need to do a pretty quick review of some concepts we learned last semester. So really quickly, looking at our periodic table, we can use this periodic table in order to predict the number of valence electrons. So just a reminder, in this first group right here, you've got one valence electron, you've got two. Remember, you can just count across. 3, 4, 5, 6, 7, 8. And this is going to be something that we use throughout this lesson today. So what I want you to do, you're going to pause me, and you're going to first answer these practice problems. So beryllium, what is its symbol? So I'm going to do the first one. So beryllium is Be, and based on its position on the periodic table, I know it has 2 valence electrons. So what I want you to do right now is I want you to pause me and complete the rest of this practice, and then we'll move on to the next page. All right, so last semester we talked about the difference between ionic and covalent bonds. And if we were in traditional class, I'd have you guys help contribute to this, but I'm gonna just fill this in here. So when I have an ionic bond, it is between a metal and a non-metal. And specifically, the metal has a positive charge, and the non-metal has a negative charge because the metal gave electrons to the non-metal. And so what forms is this crystal lattice structure, and we saw it when we looked carefully at salts. I also showed you guys the model, but basically the way I would draw this, let's say for example I have sodium chloride, the way I would draw this crystal lattice structure is I would have sodium ions, and it would be surrounded on all 4 sides by the chloride ion. This is how you can draw it. It can be as simple as that. So if I give you an ionic compound and I say draw the structure, that crystal lattice structure that I just drew, that's what we would have. And we've had experience drawing that, but now today I'm going to introduce the concept of drawing the structure for molecules. So what happens when you have molecules, they have covalent bonding. Remember, covalent bonding, this molecule is formed between nonmetals. And this is important because nonmetals share electrons. And so one's not giving electrons to the other. And so we've got to figure out how something like water forms and what in the world this line represents. And spoiler, that line represents sharing electrons. Just as a quick reminder, the reason why these elements, these 2 nonmetals, are sharing electrons, their goal is to get to the electron configuration of a noble gas, meaning they want to get 8 valence electrons. Now, when you have ionic bonding, a metal gives away electrons, so it can get 8. A nonmetal accepts electrons, so it can get 8. But when you have covalent bonding, they're sharing, so how the heck do they get to 8? And that's what we're going to address today. The only thing to keep in mind, helium is weird. Helium doesn't have 8 valence electrons like the other noble gases. Helium actually has 2. And so that's going to be important because hydrogen wants to be just like helium. And so instead of wanting 8 valence electrons, hydrogen is going to want 2. So let's figure out how to draw these molecules so that these atoms can have 8 without needing to give up electrons fully. So here are the steps. These structures, like the structure you saw for water just there, that's called a Lewis dot diagram. So I'm going to show you how to draw it, and then I'm going to do a bunch of practice simply because we're not in class together. So our first step for drawing a Lewis dot diagram is we need to count valence electrons. So we're going to count the total number of valence electrons that the molecule has. So let's do that for water. Hydrogen on the periodic table has 1 valence electron, but because I have 2 hydrogens, that's going to give me a total of 2 valence electrons, and oxygen has 6. So I have a total of 8 valence electrons. So that's step number 1. Step number 2 is I need to share electrons. these nonmetals are going to share electrons to try and help them get to 8 valence electrons. When you look at a molecule, the question becomes, how do I know what atom is at the center? And it's normally the one where you only have one atom. So when I look at H2O, I only have one oxygen. So I'm going to draw the O, and it's going to share electrons with hydrogen. Now, this line right here actually represents 2 electrons. So imagine, and I'm going to erase this in a second, imagine there are 2 electrons here. I'm going to show them as dots, and oxygen is sharing them with hydrogen. So as of right now, by sharing those electrons, hydrogen has 2 electrons from that bond. The other hydrogen has 2 electrons, but oxygen has 4 total electrons. All right? Now I need to add lone pairs of electrons, and I'll show you what that means. So remember, every atom wants 8 valence electrons except for hydrogen. Hydrogen only wants 2. And so right now, hydrogen already has those 2. It has the 2 from there. And the other hydrogen has 2 already as well. So hydrogens are happy, but oxygen is not. Oxygen has 4 electrons, but it wants 8. So what we're going to do is we're going to add lone pairs of electrons. You can draw them like this. So I have 4 already. I'm going to need 4 more. So you add them as pairs. So I'm going to add 2 on top and 2 on bottom. That gives me a total of 2, 4, 6, 8. I personally don't like drawing them as dots. It can get confusing if you're not super clear with your writing. So instead, the way that I draw this is I draw each pair as a line. Okay, so now oxygen has 2, 4, 6, 8 electrons on it. It is content. It has that 8, it has that octet. The very last step that I need to do is I need to count valence electrons again. In order to make oxygen and hydrogen happy, in order to give oxygen 8 and hydrogen each 2, I can only use 8 valence electrons. But I didn't even consider those 8 when I was drawing this, because you're not supposed to. We consider it at the end. So let's make sure I'm only using 8 valence electrons. Right now I'm using 2, 4, 6, 8. So I am good. I'm going to leave this here. I'm going to talk about the VSEPR model in a moment, but let's do one more practice problem. For PBr3, first I'm going to count valence electrons. So phosphorus has 5 valence electrons. Bromine has 7, but there are 3 bromines. So I have a total of 26 valence electrons. My next step is to share electrons. So phosphorus is going to be in the center. I only have 1 phosphorus, and then I'm going to have 3 bromines coming off of it. I don't know, something like that. Okay, so bromine, we're sharing electrons. Now I'm going to add lone pairs of electrons. So phosphorus right now has 2, 4, 6 valence electrons on it right now. It wants 8. So I need to add 2 more electrons. I'm going to add 1 pair here, and that gives me 2, 4, 6, 8 electrons. Bromine right now only has 2, but it wants 8. So I'm going to add 4, 6, 8. The bromine again has 2, 4, 6, 8. This bromine has 4, 6, 8. Everyone has 8 valence electrons now. They're happy. Now I need to count to make sure I'm only using the number of electrons I'm allowed to use, which is 26. So let's double check it. Am I only using 26 to make everyone happy? I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm good. All right. Now, I'm going to pause before I go to example 3, and I'm going to draw using the VSEPR model. What the VSEPR model tells you is that atoms are going to avoid each other. They're going to repel each other. Basically, think of it as atoms social distancing. And you can think about it because this bromine has electrons around it, and this phosphorus has electrons on it. And electrons, which are both negatively charged, repel each other. So the VSEPR model is telling you what orientation will these atoms actually take to minimize their repulsions for one another, to avoid each other as much as possible. And so you are not expected to be able to determine this completely on your own immediately. You will have this simulation. So this will be linked in the weekly schedule. You're going to click on model, and I'm going to create these models. So the first one I had was water. So water has 2 bonded atoms and 2 lone pairs. So notice, as soon as I add those lone pairs, I go from having a line to now having this bent structure. So the way I'm going to draw this, I've got them going down, and then I've got 2 lone pairs on top. So I have the oxygen on top, hydrogen's going down, and then the 2 lone pairs on top, like that. Okay, so that is the VSEPR model. You do not actually have to draw this guy at all. This is wrong. But if you draw it and then say, oh, whoops, this is actually how it should look once I do the simulation, that's totally fine. But this is what I want to actually see for your final answer. For PBr3, we're going to see what that looks like. I've got 3 bonded atoms and 1 pair. Sorry, 1 lone pair. Oops. So I got to get rid of 1 lone pair. There we go. So 1 lone pair and 3 bonded atoms. Now notice this is 3D. It looks kind of like a pyramid. I do not expect you to be able to draw this perfectly. But what I do expect is for it not to look like a T like this, because that's not what we see. We see it going down, there's another one going down, and another bromine moving down like that versus across, because these atoms are repelling each other as much as possible. So the way I would draw this, I would have phosphorus, then I'd have bromine, 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 and it would look like this. That's using the VSEPR model. All right, let's look at another practice. This one gets a little bit more tricky. So SO3, sulfur has 6 valence electrons, oxygen has 6, but I've got 3 oxygens, so I have a total of 24 valence electrons. So when I draw this, I'm going to put sulfur in the middle. I have 3 oxygens coming off of it. I'm sharing. Now I'm going to add lone pairs of electrons. This oxygen only has 2, so it needs 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Sulfur has 2, 4, 6. I'm going to add 8 to that. If we count right now, I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm using too many electrons. So here's where this gets a tiny bit tricky. Having lone pairs of electrons, for oxygen to have these 2 and sulfur to have these 2, I need a total of 4 electrons, right? This is 2 and this is 2. But by sharing, right, if I were to add another bond, we could actually reduce the number of electrons I'm needing to use. So if you ever get in this situation, you're going to draw all of this out and then say, oh no, I'm using too many electrons. If you're using too many electrons, then you will need a double bond. And just a heads up for your worksheet, you might even need to use a triple bond. But don't go to a double or a triple bond until you've made everyone happy with a single bond and then say, oh no, I'm using too many electrons. So I'm in that oh no moment. I'm using too many electrons. I'm using 26. So if I add a double bond here, what that means is sulfur has 2, 4, 6, 8, 10 electrons on it, too many. So I'm going to get rid of this lone pair here. And for this oxygen, it also has 10 on it, so I'm going to get rid of this lone pair. Now, everyone's still happy, but I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 electrons. So this is a situation, this is pretty tricky, but you guys can do it. I'm now going to draw the VSEPR model for this. So I've got 2 single bonds, and I've got a double bond. So this is what it looks like. So instead of the way that I drew it, you would have, and the double bond can go wherever you want, right? It can be on the side, but the way that you would draw this, I'm going to put the double bond on top, because why not? Double bond here, and you're going to do single bonds for oxygen. Okay, so because we're not in class, if you're like, I've got this, I'm good to go, then you can move on. And you've got your worksheet to do, 1A through H, and then on the next page, 2 and 3. If you're not 100%, totally fine. I'm gonna go back and I'm gonna do the warm up and you can do that with me. Really quickly though, for number 2, what this is saying, notice these dotted lines and these solid lines. These are just single covalent bonds. It's just showing it coming out of the page or going into the page. And so what this question is asking you to do is make sure everyone has 8 valence electrons around them. So for example, here I notice oxygen has 2, 4, so it's missing 4 electrons. So I'm gonna add 2 pairs like that. So that's all you need to do for this one. For 3, notice the way that I drew this. First of all, make sure everyone's following the octet rule. Make sure everyone has 8 that wants 8, or hydrogen has 2, which is what it wants. But the way that I do this, for example, for this carbon, it looks like a T. But remember what we just did on this practice? It should not look like a T, it should look like that. So I'm gonna redraw this whole molecule, keeping that in mind. So I'm just gonna do this first carbon with you. I've got carbon, I've got that oxygen like that, I've got hydrogen like that, and then I've got this carbon here that looks like that. So that's my way of fixing that. Okay, now you need to look at each part of the molecule and fix it, making sure you're using the VSEPR model. I would do this at the very end once you get more practice with actually drawing VSEPR models. As you work on the worksheet, please make sure you're using this site. All right, if you're not 100% right now and feel like you can do the worksheet, go back and I'm going to quickly go through the warm-up with you. All right, so let's do some practice. Ni3, nitrogen has 5 valence electrons. Iodine has 7. So I have a total of 26 valence electrons. Next step is share. So I've got nitrogen, I've got 3 iodides coming off of it. Next step is add lone pairs of electrons. I want everyone to have 8. So iodine right now has 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. Now I'm going to go back and make sure I'm only using 26 valence electrons. 2, 4, 6, 8. So I'm actually going to show my counting here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm good. Now I need to use my VSEPR model and make sure I do this correctly. I've got 1 lone pair of electrons. I've got 3 single bonds. So it looks like this. So instead of the T that I drew, it should have looked like this. And you'll get to the point in practice where you know what it's going to look like in advance. So it does not look like that. Okay, so that's the first one, CS2. Let's do it. Carbon has 4 valence electrons. Sulfur has 6, but I have 2 sulfurs, so I have a total of 16 valence electrons. Carbon is going to be in the center. I'm sharing electrons with sulfur, and now I'm going to make everyone happy with lone pairs. So 2, 4, 6, 8, 2, 4, 6, 8. Carbon already has 4, so it needs 4 more. Now I'm going to count to make sure I'm using the correct number of electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm using way too many. I should only be using 16. Now and only now do I use a double bond. Don't use a double bond until you get to this point here where everyone's happy and I'm now just doing my check and I'm using too many. So I'm going to do a double bond here. Carbon has 2, 4, 6, 8, 10, so I'm going to get rid of a lone pair of electrons and a lone pair of electrons on this sulfur. Now let's double check to make sure I'm good. 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm still using too many, so I'm going to add another double bond. Carbon now has 10, so I'm going to get rid of that lone pair and this lone pair. Everyone has 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay. How many electrons am I using? 2, 4, 6, 8, 10, 12, 14, 16. I'm good. Now let's check to see how this should look. I've got 2 double bonds, 1, 2, and it looks like a very nice little line right there. Look at that. And that's exactly how I made it in my drawing. So that works great. All right, NO3 minus. This minus tells me that I need one additional electron. So if I need one additional electron, I've got 5 valence electrons from nitrogen. I've got 3 oxygens, which have 6 valence electrons. And then to all of that, I'm going to simply add 1. So when I add all of these together, that gives me 24. So nitrogen's in the center. I'm going to have oxygens coming off of it. I'm going to share. I'm going to add lone pairs of electrons. 2, 4, 6 on nitrogen, so I'm going to add 1 pair. I'm going to add 3 pairs on each oxygen. And right now, when we count, I am using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm using too many electrons. So now and only now, I say, okay, I'm going to need a double bond. So I'm going to add a double bond here. Doesn't matter where you add it. Nitrogen now has 10, so I got to get rid of a lone pair. This oxygen has 10 as well, so I'm going to get rid of a lone pair. When I redraw this, oh, sorry, I'm going to recount. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm good. When I redraw this, I've got 1 double bond, 2 single bonds, and it looks like that, which looks wonderful. It's that little kind of a triangle. So I'm going to draw this. I've got nitrogen, oxygen, like that. All right, and if you have further questions, if you've watched all of this warm up and you still have further questions, send me an email and I'm happy to help.